This is how you solve a polarity problem. The question we are being asked is how many of these molecules are polar. There are three basic steps we will use to solve the problem. Draw the Lewis structures, identify bond dipoles by using differences in electronegativity, and identify net molecular dipoles based on molecular geometries. Let's begin to solve the problem for each molecule one by one. We can do this correctly by using the rules we learned about Lewis structures. SO3 is the first molecule we will look at to decide if it is polar. There's a total of 24 valence electrons. To draw the Lewis structure, we begin placing the valence electrons in the outside atoms first. We have to make sure each atom has an octet. We have used all 24 electrons, however, the S atom does not have a full octet, so we'll have to make a double bond in between the S and the O atom. Now let's look at the bond dipole. The highest electronegative atom, which is O, will have partial negative charges because the electrons drift towards the atom with the highest electronegativity. That means there'll be a partial positive charge on the S atom. The bond dipoles are going to look like this. A tail that's positive on the S towards the O on the outside. There'll be two other dipoles going this way and this way. The arrows show you the direction of the charge separation, and the length of the arrow represents the magnitude of the charge separation. In order to find out whether the bond dipoles cancel or not, we have to look at the three domains around the central atom. Three domains is a trigonal-planar molecular geometry. Since all of our domains are the same, we will have no net dipole, and since there is no net dipole, this molecule is nonpolar. Next, we will look at OF2 to see if it is polar. There's a total of 20 valence electrons. Draw the Lewis structure by placing the valence electrons in the outside atom first. We have used all 20 electrons and each atom has an octet. Now we will look at the bond dipole. The highest electronegative atom, which is F, will have partial negative charges because the electrons drift towards the atom with the highest electronegativity. This means there will be a partial positive charge on the O atom. The bond dipoles are going to look like this. In order to find out whether the bond dipoles cancel or not, we have to look at the four domains around the center atom. Since there are four domains and two of the domains are lone pairs and two of the domains are bonds, OF has a bent molecular geometry. We have an F and two O's on the outside, so the dipoles go from the O out to the F's. Because of the molecular geometry, the net dipole will be going down. The dipoles in the bond don't cancel because of the molecular geometry being bent. There is a net dipole in this molecule, so it is polar. Now we will look at BeCl2 to see if it is polar. There is a total of 16 valence electrons. We have used all 16 electrons, but the central atom Be does not have an octet. This is okay because Be is an exception to the octet rule. Now let's look at the bond dipole. The highest electronegative atom is Cl, so it has a partial negative charge. This means there will be a partial positive charge on the Be atom. In order to find out whether the bond dipoles cancel or not, we have to look at the two domains around the center atom. Since there are two domains on the central atom, the molecular geometry is linear. Since all the domains are the same, there is no net dipole, making this nonpolar. Now we will look to see if CCl4 is polar or nonpolar. There's a total of 32 valence electrons. We have used all 32 electrons and the central atom has an octet. Now we'll look at the bond dipoles. The highest electronegative atom, which is Cl, has partial negative charges. That means there will be a partial positive charge on the C atom. There will be three other dipoles going this way, and this way. In order to find out whether the bond dipoles cancel or not, we have to look at the four domains around the center atom. Four domains is a tetrahedral molecular geometry, and since all of our domains are the same, we'll have no net dipole, which means this is a nonpolar molecule. Lastly, we'll look at O3 to see if it is polar or nonpolar. There's a total of 18 valence electrons. We have used all 18 valence electrons, but the central atom O did not have an octet, so we had to use a double bond, and you can either use it between these two O's or these two O's. For this specific molecule, we will not look at the bond dipoles because all of the atoms have the same electronegativity. Since there are three domains, and one of the domains is a lone pair, and two of the domains are bonds, O3 has a bent molecular geometry. Because of the molecular geometry, the net dipole will be going down. The dipoles in the bond don't cancel because of the molecular geometry, so since there is a net dipole, the molecule is polar. Now we will look at the problem again. The original problem asked how many of these molecules are polar. 3 of the molecules were nonpolar because there was no net dipole, and 2 of the molecules were polar because all the domains were not the same. Some common mistakes that can occur when solving this type of problem are: people sometimes draw the Lewis structure wrong because they may have counted the number of valence electrons incorrectly. Oftentimes, people forget the exceptions to the octet rule, which could lead to putting the wrong number of valence electrons around the center atom.